Hey everyone, and welcome back to the Explorer Zone. As always, we're coming to you from the Science Mill, and you can find us online at sciencemill.org. Today, we're going to be combining math and art with a look at two of our favorite exhibits, the wave pendulum and the Wondergraph. On the surface, it might seem like math and art are totally unrelated, but actually, they're very closely intertwined. Master artists have used mathematics to create legendary works of art. Take Leonardo da Vinci, for example. Some of his most famous works are based on mathematical formulas. His Vitruvius Man examines the mathematical proportions needed to draw an anatomically correct human body. In addition, his most famous portrait, Mona Lisa, contains multiples of algebraic constants called the golden ratio. And while artists use math in their craft, some mathematicians and physicists use an art to convey ideas as well. Let's head over to Wendy to hear more about how physics and art can interact.
Hey everyone, my name is Wendy and I'm the Assistant Director of Education here at the Science Mill. Today we are going to explore how you can use the physics of a pendulum to create art. Physicists study energy, matter, and motion. They use art to help them visualize abstract aspects of the physical world. Our wave pendulum exhibit creates a beautiful pattern of motion due to the unique length of each pendulum. Because of the varying lengths of each pendulum, they will oscillate or swing at different speeds when dropped. They start out of sync, but eventually sync back up based on an algebraic formula. It's not a coincidence or luck, it's physics visualized. Artists, in turn, can use physics to better understand and experiment with their materials. Biophysicist Pupa Gilbert's research has even expanded artist ideas about colors. She uses physics and spectroscopy, that's the study of light dispersal, to find new pairs of complementary colors. Ready to tap into your inner artist and physicist? Here's a hands-on pendulum activity to try at home. Welcome to the Learning Lab. I'm going to show you some basic materials that you can use to make your own pendulum painting cup. You can go online to our website at sciencemill.org and to our Explorer Zone page to download complete materials list as well as detailed instructions for this activity. Materials that you will need to make your pendulum painting cup are about a 10-ounce plastic cup. You want a thumbtack, some washers, a large paper clip, masking tape, some string, paint, Dixie cup or other cup to mix your paint to the correct consistency, and some duct tape. So let's get started. Using your thumbtack, you are going to make a hole, puncture in the center of the bottom of the cup, about the size of a ballpoint pen. Then you'll use the thumbtack to poke 2 holes on opposite sides near the top lip of the cup. Once you have the holes poked in your cup, you will take your large paper clip and you want to put it into the shape of a W. It doesn't have to be perfect, but you want it to look something like this. You will stick the ends of that paper clip in the holes of the cup. You may need to adjust that hole size if it doesn't fit. You want to use a washer, some sort of weight that you can slide onto the paper clip, and then you will put it inside the holes in your cup. All right, so once you have the ends of your paper clip through the holes near the top of the cup, you're going to want to cover the hole at the bottom. That's kind of the stopper for your paint. So you'll use a piece of masking tape to cover the hole at the bottom until you're ready for your paint to come out for your painting. And then you want to take a string and you're gonna tie the string to the washer. And then your completed pendulum should look something like this. Now to prep your paint. The paint should be the consistency of ink. So with tempera or acrylic paint, it takes about a 1-to-1 ratio of water to paint. It needs to be thin enough to escape through the hole in the bottom of the cup, but thick enough so that it doesn't all just pour out all at once. So now it's time to set up your pendulum and get ready to paint. You want to prep an area with a table. You want to place a large plastic tablecloth, some other protective material underneath the pendulum area to protect the flooring. You also need to have a large piece of paper about 2 feet by 2 feet, and you want to make sure that you use duct tape. You want to have that cup secured by the loose end of the string on the underside of the table and have it hanging centered over your paper. Before you begin, experiment with the height and angle of your pendulum swing. Make sure your paper and your protective covering are in the right position to catch all of the paint. Pour your paint into the pendulum painting cup. Once you are ready, lift the pendulum painting cup to the starting position of your choice, remove the tape, and let it swing. We are just doing a simple demonstration, but you can download from our website a document that shows you how to set up a science experiment where you can make 3 paintings changing your pendulum variables, like adding mass, changing the length of your pendulum string. You could even make multiple pendulum painting cups and use different swings of each pendulum, layering different colors and different patterns on top of each other to create a pendulum painting masterpiece. Another place where art and math mingle here at the mill is in our Wondergraph exhibit. This wacky contraption creates beautiful spirals and different geometric patterns based on the angles of its arms. You may be familiar with a cousin of our Wondergraph, the spirograph. The spirograph uses interlocking gears to create designs. Hypotrochoids are the spirals made by a small gear rolling inside a larger one, while epitrochoids are spirals made by rolling outside. Spirographs first became popular in the 1960s, but Wondergraphs actually date back to 1907. And instead of gears, Wondergraphs are controlled through a pulley system. Our Wondergraph designer, Craig, is joining us online from California to share some behind-the-scenes secrets about this exhibit.
I'm Craig Neuswanger. I live in Oakland, California with my wife. We have a neat studio here in Oakland. So I've been in optics and holography most of my career, and that's a long story, as you can imagine. We'll probably talk about that at another time. But I've had an interest for years in producing interesting machines and contraptions that illustrate essential physical and mathematical concepts, and to inspire people and children and anyone really to ask a few questions and look a little deeper. I did a talk which you folks have, which is called Drawn to Wonder, and it's kind of an essential idea of mine that if you can experience something that opens your eyes just a bit, it opens your mind to the new idea and to learning. And so that's my concept. That's what I like to do. Well, including I would say ones that I've finished and I've keep using. I have actually 3 set up right now in our studio. I've been doing some new things with them. One was a tabletop version which I made for maker fairs and so on. And then I made one for a gallery show, which unfortunately didn't happen, but it's the larger machine, which I sent you some video of that. And so really primarily 3. And then this Wondergraph here I made as a prototype for the one that I made for the Science Mill, which the Science Mill version is just a few inches bigger. Which I think the part of the idea when you build something for this kind of situation is you boil it down to the essence of what it needs to be, to where it has enough interest and experience that the person has very quickly. And they know, for example, I just added this to mine. I added it's called pink ivory, the handle for the unit at the science mill is made of this very rare hardwood, which is pink. And so when you walk up to the device, you don't have to know, no one has to tell you what to grab to start using it. So it's those kinds of things that I think a lot about. My interest in these kinds of devices and imagery goes a long way back. I've had an interest in various kinds of machines that do interesting things, and certainly machine tools and devices that were used for other purposes. I also had an early experience with a company that did laser shows where we scanned patterns on the ceiling of a planetarium. It was called Laserium. And we used these patterns quite often in the imagery. And so this has been this thread. And so at some point, I'd been thinking about doing more engraving devices and machines. And I also had an interest in motion, robotic motion and motors and electronics and so on. And so I had thought about making a more intricate machine for engraving metal. And then it went from there when my brother sent me for my birthday one time. He found this Hootenanny Magic Designer toy in a shop, and he bought it for me. That I'd also there was this article or part of a book series called The Boy Mechanics. The Boy Mechanics. There are 3 versions of this, and it's available in PDF form online. It's unfortunate to be called The Boy Mechanic, not the Children's Mechanic, but that was the age they were written in. Tons of great ideas in these books, great fun stuff. But in one part, they have a device they called the Wondergraph. And so it was described in this book in 1913. And so there's one particular design that kind of rang a bell to me and was similar in design to the Wondergraph. And so I took these ideas and distilled them into what you see now, the Wondergraph. There are these kind of essential ideas in math that go back quite a long time, and you'll see a photo in which I'll send you, and you can put in here. There was a fellow named Antoine Lissajous, and Lissajous was interested in harmonic relationships. And here is a set of patterns that he was exploring which reveal harmonic relationships between 2 sine waves. And so he created a setup with tuning forks with mirrors. So one tuning fork vibrated in one direction, and the other one vibrated at 90 degrees to it. And they projected the light from a candle or gas flame off these 2 mirrors, and these patterns appeared on the wall that revealed a immediate graphical relationship between the frequencies. And so in both the Wondergraph in a way and some of my other machines tend to be, they have a relationship of about 90 degrees to the center of this turntable. But in effect, these 2 cranks create a sine wave by their nature. So when the rotational motion is converted to a somewhat linear motion on these arms, then it combines these 2 sine waves in a complex way. Describing that, in that these systems that I build are not perfect, and they're not perfectly 90 degrees, that actually increases the complexity of the math required to describe the motion. And since this is a continuous kind of motion, you either break it into little periods, or you use calculus and so on to figure out what's going on. But in essence, And there's some nice animations you can see where you divide a circle into equal parts, and then you translate the circular motion into a linear motion, and you can see that sine wave revealed. It's quite a beautiful description. And it doesn't require an understanding of the mathematics. It gives you an intuitive sense of the relationship of the mechanical motion of the cranks to the motion of the pen. I would like to touch on the difference between what this is and what a spirograph is. Often when someone comes to see one of these machines, they immediately say, oh, this is like that thing I had when I was a kid. What was that called? And I say, spirograph. And he goes, yeah, spirograph. And so there is a difference in that what the Wondergraph and what my other drawing machines do is really they draw these Lissajous figures, but then I rotate the paper. And so, for example, if you look in these patterns, I don't know if you can see this, I can come in closer after this. And you see this figure 8 pattern in this chart. And then you see the figure 8 laid out in this drawing here. Basically what I'm doing is I'm taking that Lissajous figure and I'm rotating it around in a symmetrical way. And that's where a lot of the complexity comes in these drawings. Also the fact that the machine is imperfect, so that every time it makes one revolution of the turntable, the relationship of these turning cranks is slightly different every time it goes around, so that it keeps making a more complex pattern. If it was perfect, then it would be more like the Hootenanny toy, where the relationships are fixed because it uses gears. This uses belts and pulleys, and it's actually that's an advantage for this particular gadget. Well, thank you for the opportunity to share my work with you guys. I know it's in these times it's people can get a little cabin fever, but if you can find some things like this to explore and experiment with and make something with your hands, get out the cardboard and the glue and paper clips and make something fun. So thanks again.
Geometry is an essential element in many kinds of art. You can find geometric patterns in mandalas, on the carpet of floors, within the pillars of ancient structures, or even in the ways figures are posed. Today, instead of sculptures or paintings, we are using geometry to make something beautiful but temporary, bubbles. For this activity, again, you can go online to our website to download the complete materials list and detailed instructions for the activity. You will want to gather materials that you can use to make a geometric bubble wand. We found that fuzzy sticks and straws really work well, but experiment at home, maybe try craft sticks, or even build your geometric wand from Legos or K'NEX pieces. Be creative. You will also need a plastic container. You can use any plastic tub. We've used a 5-gallon bucket. You could use a small plastic trash can. You could even use a shoebox. Just make sure to use a crock-pot liner or a trash bag, and then secure it on the outside with tape so your bag doesn't collapse when you fill it with your bubble solution. You can certainly use pre-made bubble solution, or you can make your own. The general recipe is 1/2 gallon of water and 1/2 cup of dish soap. We found that Dawn works best, but you can use the dish soap that you already have at home. Adding in an optional ingredient, a tablespoon of glycerin or a tablespoon of white Karo syrup, can help make your bubble solution thicker and slimier, but this is not a requirement. When making your bubbles, fill your container with water first, then add your other ingredients. Be sure to gently mix. Do not stir vigorously. You don't want to make too many bubbles. Once it's mixed, you'll want to scrape off all of the foam off the top of your bubble solution. If you can make it ahead of time and let your bubble solution sit undisturbed overnight before using it, that will make an even better bubble solution. Now make your geometric bubble wand. Choose the geometric shapes that you want to build. Make a variety. You will want to compare the different bubbles that each one makes. Don't forget to make a handle for your bubble wand. You'll want to form frames using straws for the straight pieces, and you can connect the straws by folding fuzzy sticks into a shape similar to this. And now for the fun part. Try different techniques. Try dipping the entire geometric shape under the bubble solution. Try dipping just one face of the figure, or even dipping it at an angle with one of the vertices in the bubble solution first. Be sure to observe your geometric wand after you remove it from the solution to investigate the shape of your bubble that forms before you blow the bubble. That's when you'll get to see the geometric bubble that forms. Now, you can also experiment by blowing your bubbles using a straw. You'll dip one end of the straw in the bubble solution, insert that end into the bubble formed on your geometric wand, and then blow air inside through the straw to see what happens. So don't forget to share all of your geometric, bubble, and pendulum painting creations with us at programs@sciencemill.org. Tag the Science Mill when you post your creations on Facebook, Twitter, or Instagram. Visit our website to find more DIY activities and games, as well as career connections for this episode. Speaking of which, it's time to take a final look at some careers that blend art with science.
As we saw today, math and art can exist together to make some really groovy designs. One career that combines math, art, and physics to create three-dimensional structures is architecture. Architects design and oversee the construction of buildings. To become an architect, you will need to have a strong eye for detail, artistic ability, and understand how to problem solve using physics. Another career where an artistic eye is important is web design. Not only do web designers make sure websites are user-friendly and easy to navigate, they have to ensure the computer code and formulas that run things behind the scenes are functional. This takes a dash of artistic creativity and a working knowledge of how code and math interact. Sometimes it's hard to understand large amounts of data just by looking at it. That's where a scientific visualization specialist comes in. Using computer science, a scientific visualization specialist can take huge sets of data or mathematical formulas and translate them into graphics that are easy to read and understand. This can be in the form of animations, simulations, and even 3D modeling. A well-designed visual aid can enhance our understanding of abstract ideas.
Take a close look at the world around you and see where you can find art and math. The pattern on your favorite sweater, the design of a staircase, a neighbor's wind chimes. You may be surprised at all the ways they combine. And don't forget to send in your videos from last week's Rube Goldberg Challenge to programs@sciencemill.org. That's all from the Science Mill for this week. Remember, you can find all of our DIY activities and career guides for this episode and other episodes on our website under the Explore Zone tab. We'll see you next Tuesday.